The universe is not endless in the way it first appears. Even as space stretches outward in every direction, even as time carries light across billions of years, there are quiet boundaries written into reality itself, limits that cannot be crossed by speed, by size, or by knowledge. Tonight we'll move gently toward those edges, not to challenge them, but to understand why they exist at all. If this calm journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these quiet explorations alive, and I hold that support with sincere thanks. Now, we drift into the first truth. Part 1. The speed nothing can outrun. Nothing in the universe moves faster than light. Even as galaxies rush apart and particles vibrate with unimaginable energy, this single speed remains absolute. It isn't just a limitation of technology or perception, it is woven into the structure of space-time itself. To understand why this boundary exists, we begin with a universe where motion and time are inseparably linked. Even as you lie still, breathing slowly, light is already on its way from distant stars, traveling across space with unwavering consistency. For more than a century, physicists have measured this speed with increasing precision, roughly 299,792 kilometers every second, not approximately, not on average. Always. No matter where you are, no matter how fast you move, light's speed remains the same. This quiet certainty is one of the most profound discoveries in science, and it reshaped how we understand reality itself. Before this realization, motion seemed simple. If you ran toward a beam of light, common sense suggested you should see it move faster. If you ran away, slower. That's how every other speed works in daily life. But experiments in the late 19th century refused to obey that intuition. No matter how scientists chased light, no matter how Earth moved through space, light's speed never changed. It was as if the universe was protecting a secret. In 1905, Albert Einstein offered an explanation that would forever alter physics. He proposed that space and time were not separate arenas where motion played out, but a single connected fabric called spacetime. To keep the speed of light constant for all observers, something else had to give. And what gave way was time itself. If you move faster through space, time slows down. Not symbolically, not metaphorically, literally. Clocks tick more slowly for objects in motion compared to those at rest. This effect, known as time dilation, has been measured countless times. Atomic clocks flown on airplanes return slightly out of sync with those left on the ground. Satellites orbiting Earth must constantly correct their clocks to account for their speed. Without this correction, GPS navigation would drift by kilometers each day. The speed of light is not simply fast, it is a conversion factor between space and time. It tells the universe how much time must stretch to preserve causality. Because if anything could move faster than light, cause and effect would break down. Events could occur before their causes. Information could arrive before it was sent. The universe would lose its ability to remain coherent. Light, in this sense, is not just illumination. It is the messenger that defines what can influence what. Anything that happens here can only affect regions of space that light has time to reach. This boundary is known as the light cone, an invisible structure surrounding every event. Inside it, cause and effect are possible. Outside it, they are forever disconnected. Even gravity obeys this rule. Although it feels immediate, changes in gravity propagate at the speed of light. When massive objects move, space-time ripples outward as gravitational waves, traveling no faster than light itself. In 2015, detectors on Earth measured these waves from colliding black holes more than 1 billion light-years away. The signal arrived exactly when light would have, confirming once again that nothing outruns this cosmic limit. You might wonder why light of all things holds this role. After all, light has no mass, and that absence is key. According to Einstein's equations, as an object with mass accelerates, it requires more and more energy. The closer it gets to the speed of light, the more energy it demands until the requirement becomes infinite. No finite process can supply infinite energy. And so, massive objects can approach the speed of light, but never reach it. Particles and accelerators illustrate this beautifully. At facilities like CERN, protons are pushed to energies so high they circle underground rings at speeds within a tiny fraction of light speed. As engineers add more energy, the protons do not move significantly faster. Instead, their mass increases, their momentum grows, and space-time itself responds. The universe refuses to let them cross the line. Light does not slow down or speed up because it exists differently. For a photon, the journey from emission to absorption takes no time at all. From its perspective, time does not pass. Distance collapses. Emission and arrival are the same event. This idea is difficult to grasp, but deeply calming when you let it settle. Light is not racing through time, it simply exists along spacetime's geometry. This also means that when you look into the night sky, you are not seeing things as they are, you are seeing them as they were. Light from the moon is about 1 second old. Light from the sun is 8 minutes old. Light from distant galaxies may be billions of years old. The speed limit of light turns the universe into a layered archive where distance is also history. And yet, even with this limitation, the universe appears vast beyond comprehension. Galaxies move away from each other as space itself expands. Some of them recede so quickly that their light will never reach us, not because it travels too slowly, but because the space between us grows faster than light can cross it. This does not violate the speed limit. It reveals something even subtler. The expansion of space is not motion through space. It is space itself changing scale. This distinction matters. Objects cannot move through space faster than light, but space can expand without limit. This is why the universe can be larger than the observable region, why horizons exist, why there are places that will remain forever beyond contact. The speed of light quietly defines not only motion, but knowledge. As you rest here, it's worth noticing how gentle this limit feels. It does not shout, it does not threaten, it simply exists, steady and universal. Every particle, every wave, every force respects it. It keeps the universe ordered, predictable, and safe from paradox. Without this limit, stars could destabilize instantly. Information could jump unpredictably. Reality would lose its continuity. The speed of light is the universe's way of preserving coherence, a maximum not imposed from outside, but emerging naturally from how spacetime is built. And there is something comforting in that. A reminder that even at cosmic scales, not everything is unbounded, that infinity is approached carefully, never reached recklessly, that there are edges not meant to be crossed, but understood. As we continue this quiet journey, one question remains, lingering gently at the edge of perception. If nothing can outrun light, and distance is also time, how far can the universe truly reach us at all? Part 2. The edge of the observable universe. There is a horizon beyond which we can never see, not because our telescopes are weak, but because light itself has not had enough time to reach us. The observable universe is not the whole universe, only the part that is spoken to us so far. Beyond that glowing shell lies a silence that may never be broken. As you rest quietly, imagine light traveling toward you from every direction. Some of it began its journey moments ago, reflecting off nearby walls or drifting in from the moon. Some of it has been traveling for years, centuries, or millions of years. And some of it began its journey before Earth even existed, long before the sun formed, when the universe itself was still young and cooling. All of this light arrives together, meeting you in a single moment. But beyond a certain distance, no light has arrived at all. That boundary is not a physical wall. There's no edge you could touch, no curtain you could pull aside. It is a limit defined by time. The universe has a finite age, about 13.8 billion years, and light has a finite speed. That combination creates a horizon. We can only see as far as light has had time to travel since the beginning of cosmic expansion. This is what scientists call the observable universe. It is a sphere centered on you, extending outward in all directions, not because you are special, but because observation always begins where the observer is. If you were standing on a distant galaxy, your observable universe would look different, centered on that location instead. Every point in space carries its own horizon. The radius of this observable universe is not 13.8 billion light-years, as intuition might suggest. Because space itself has been expanding while light traveled through it, the most distant visible regions are now about 46 billion light-years away in every direction. The light left them long ago, but the space between us has stretched continuously since then. Distance, in cosmology, is never as simple as it feels. When astronomers look toward the deepest reaches of space, they are not looking at emptiness. They are looking at the earliest chapters of cosmic history. Galaxies appear smaller, younger, more chaotic. Stars are hotter and more massive. Structures are just beginning to take shape. At the very edge of visibility, galaxies disappear altogether, replaced by a faint uniform glow. This glow is the cosmic microwave background. It is the oldest light we can see, released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, and light was finally able to travel freely. Before that moment, the universe was opaque, filled with a hot plasma that scattered photons endlessly. Light existed, but it could not go anywhere. The cosmic microwave background is not light from stars or galaxies. It is light from space itself, stretched and cooled over billions of years until it now glows softly in microwaves. It arrives from every direction with astonishing uniformity, differing in temperature by only a few millionths of a degree. Those tiny variations are the seeds of everything that followed. Beyond this background, there is nothing we can see, not because there is nothing there, but because no information from earlier times can reach us. The universe has placed a limit on what can be known through observation, a natural horizon formed not by barriers but by beginnings. And yet, even this horizon is not fixed. As time passes, the observable universe grows. Light from regions that were once beyond reach eventually arrives. New galaxies enter our view. The horizon expands outward, slowly revealing more of the cosmos. But there is a quiet counterbalance to this growth. The universe is not just expanding, its expansion is accelerating. Driven by dark energy, space itself stretches faster and faster over time. This means that while some regions come into view, others slip away forever. There are galaxies whose light we see today that will never be able to send another signal to us again. They are already receding too quickly. This creates a second kind of boundary known as the cosmic event horizon. It marks the farthest distance from which light emitted now can ever reach us in the future. Anything beyond that distance is causally disconnected, not just temporarily, but permanently. No matter how long we wait, no message from beyond that horizon will arrive. The universe, then, has both a past horizon and a future horizon. One defines what we can see now. The other defines what we can ever interact with. Between them lies everything we will ever know through light and gravity. This can feel unsettling at first, the idea that there are regions of reality forever beyond reach. But there is also something deeply peaceful about it. The universe does not demand that everything be accessible. It allows mystery to remain. It permits silence. From a scientific perspective, these horizons are essential. Without them, the universe would be unstable. If information could propagate infinitely fast, small fluctuations could influence everything instantly, destroying the gradual formation of structure. Horizons protect causality, just as the speed of light does. They localize influence, allowing galaxies, stars, and planets to form quietly over time. As you breathe, consider that the air around you has its own horizons. Sound travels only so far. Heat diffuses gradually. Even on Earth, influence is limited by speed and distance. The cosmos simply extends this principle to its grandest scale. Astronomers use careful measurements to map these boundaries. By studying how galaxies cluster and how light stretches as it travels, they reconstruct the geometry of space. Satellites like WMAP and Planck have measured the cosmic microwave background with exquisite precision, confirming that the universe is remarkably flat on large scales, and that its observable horizon is well defined. Yet even with all this knowledge, humility remains essential. Everything we infer about the universe beyond our horizon is indirect. We assume that the laws of physics are the same everywhere, that the universe continues beyond what we see. These assumptions are reasonable, supported by consistency and symmetry, but they remain assumptions. There could be regions vastly different from our own. Other cosmic patches with different initial conditions, perhaps even other horizons, overlapping in ways we cannot detect. The observable universe is not the universe. It is a sample, a window, and windows are meant to frame, not to contain. As night settles around you, it can be comforting to know that the darkness beyond the stars is not emptiness. It is simply distance, time, and patience, a reminder that knowledge unfolds slowly, bounded by the speed at which the universe allows itself to be known. We live inside a glowing bubble of information, expanding gently with each passing moment. Every second, new light arrives, new ancient messages reach us. The universe continues to speak, quietly, steadily, one photon at a time. And as we continue this calm journey outward, another question waits just beyond the horizon. If the universe extends farther than we can ever see, then what does distance truly mean when space itself is still growing? Part 3. When distance stops, meaning anything. If you could keep zooming outward forever, space would begin to behave strangely. At the largest scales, distance loses its familiar meaning as expansion stretches reality faster than light can travel. Galaxies are not simply far away, they are being carried away by space itself, creating limits no journey can overcome. At first, distance feels intuitive. A few steps take you across a room, a few hours carry you across a country. Light years stretch between stars, but they are still just longer versions of the same idea, separation, measured by how long travel would take. Yet when we follow this logic outward into the deepest reaches of the universe, it quietly breaks down. Distance, it turns out, is not a fixed thing. It is something that changes with time. In everyday life, space feels static. The ground beneath you does not stretch as you breathe. The walls do not drift apart, but on cosmic scales, space itself is dynamic. It expands, not into anything, but everywhere at once. This expansion is not like an explosion from a central point. There is no center. Every location sees all distant galaxies moving away, as if the universe were inflating uniformly in all directions. This idea can feel abstract, so physicists often describe it gently. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No dot is special. None sits at the center of the expansion. The surface itself is growing. In our universe, galaxies are like those dots, and space is the balloon. Because of this, galaxies can recede from one another faster than light without violating the cosmic speed limit. They are not traveling through space at that speed. Space itself is expanding between them. Light still obeys its limit locally, but the stage on which it travels is stretching beneath it. At small distances, this expansion is negligible. Gravity binds stars into galaxies and galaxies into clusters. Within these structures, space does not expand in any meaningful way. The Milky Way is not being torn apart. The atoms in your body are not drifting away from each other. Gravity and other forces easily overcome expansion on these scales. But as you look farther and farther out, gravity weakens. Structures become looser. Eventually, expansion dominates. Galaxies are no longer bound together. They drift apart, carried by the growth of space itself. Beyond a certain scale, there is no force strong enough to hold matter together against the expansion of the universe. This is where distance begins to lose its simple meaning. When a galaxy is billions of light years away, asking how far it is becomes complicated. Do you measure the distance when the light was emitted, when it arrives, or how far away the galaxy is now after billions of years of expansion? Each answer is correct in a different sense. Cosmologists use several definitions of distance, each carefully chosen for a specific purpose. There is co-moving distance, which factors out expansion and tracks positions in the cosmic grid. There is proper distance, which measures separation at a given moment in cosmic time. There is luminosity distance and angular diameter distance, each tied to how light spreads and how objects appear. These definitions exist because space itself is changing. Distance is no longer a static ruler laid across an unchanging stage. It is a relationship between events, stretched and reshaped by time. As expansion accelerates, this stretching becomes more dramatic. Observations of distant supernovae in the late 20th century revealed that the universe's expansion is speeding up, not slowing down as once expected. Some unknown component, now called dark energy, permeates space and drives this acceleration. Dark energy does not clump, it does not form stars or galaxies. It acts uniformly, pushing space apart more strongly as space grows. The more universe there is, the more expansion it generates. This creates a future where distant galaxies slip away faster and faster, eventually disappearing beyond the cosmic event horizon. In that distant future, observers in our galaxy will see fewer and fewer galaxies. The night sky will grow darker, quieter. Eventually, only the local group of galaxies, bound together by gravity, will remain visible. Everything else will have crossed a boundary beyond which light can never reach us again. Distance, in that sense, becomes absolute, not because things are infinitely far, but because they are causally disconnected. No signal, no journey, no influence can bridge the gap. The universe quietly edits itself, limiting what can be reached. This challenges our deepest intuitions. We often imagine that with enough time and technology, any distance can be crossed. But cosmology teaches us that some separations are permanent, not because of barriers or walls, but because the geometry of spacetime itself forbids connection. Even light, patient, and relentless cannot overcome this. Photons emitted from beyond the event horizon will forever lose ground as the space between source and observer grows faster than they can traverse it. They move at light speed locally, but globally, they fall behind. This does not mean the universe is finite. It may extend far beyond what we can ever observe. It may even be infinite, but infinity, if it exists, is not something we can approach step by step. It is not reachable by accumulation. It remains conceptual, not experiential. As you lie here, consider how different this is from the universe imagined in earlier centuries. Once, space was thought to be fixed and eternal. Distances were absolute. Time flowed the same everywhere. Motion unfolded against an unchanging backdrop. That picture has gently dissolved. In its place, we now see a universe where space stretches, time bends, and distance depends on when and how you measure it. A universe where separation is not just about where things are, but about how reality itself evolves. And yet, there is a subtle calm in this realization. The universe is not racing chaotically outward. Its expansion is smooth, measured, governed by simple equations. The same laws apply everywhere we can see. The same patterns repeat across billions of light years. This consistency allows scientists to model the cosmos with remarkable accuracy. By measuring how fast galaxies recede at different distances, they reconstruct the universe's history and predict its future. They infer how space expanded in the past and how it will stretch in the ages to come. These models tell us that distance will continue to lose meaning in one particular way. In the far future, most of the universe will become unreachable, not just unseen. Each galaxy will exist in its own island of space, surrounded by darkness. But this is not something to fear. It is simply a reflection of how spacetime unfolds. The universe is not closing in or collapsing. It is opening, slowly, gently, creating more room than any traveler could ever cross, and within that opening, there is still intimacy. Locally, stars orbit, planets form, life reflects, meaning exists at small scales, where forces balance and connections endure. The loss of distant reach does not diminish what is near. Distance stops meaning anything only when we insist on treating the universe as a static place. When we accept it as a dynamic process, distance becomes a story rather than a number, a narrative written by expansion, gravity, and time. As we continue this quiet journey, another boundary comes into view, even more subtle than the last. If distance itself can stretch beyond meaning, what happens when we look not outward but inward, toward sizes so small that space itself may begin to dissolve? Part 4. The smallest possible length. There is a size below which space may no longer exist. At the Planck length, our best equations fall silent. Space stops being smooth, time flickers, measurement itself loses meaning. This isn't a technical barrier, it's a fundamental one, where reality refuses to be divided any further. If you imagine zooming inward, past landscapes and skin and cells, the journey feels familiar at first. Objects become smaller, but still recognizable. Molecules drift into view, then atoms, mostly empty space with a dense nucleus at their center. Zoom further, and the nucleus itself resolves into protons and neutrons, each composed of quarks bound by invisible forces. At every step so far, the universe has rewarded curiosity with deeper structure. For more than a century, physics has followed this path inward with extraordinary success. Each increase in resolution revealed new layers, new particles, new rules. It was tempting to believe this process could continue forever. That if we simply built more powerful instruments, reality would keep unfolding without end. But when physicists followed their equations all the way down, they encountered something unexpected. A limit not imposed by technology, but by nature itself. That limit is known as the Planck length, about 1.6 or 1035 meters, a number so small that it resists intuition. If an atom were expanded to the size of the observable universe, the Planck length would still be smaller than a grain of sand in comparison. It is not merely tiny, it is extreme. The Planck length is not chosen arbitrarily. It emerges when three fundamental constants of nature are combined: the speed of light, Planck's constant, and the gravitational constant. Together, they define a scale at which quantum mechanics and general relativity collide. Below this scale, our two best descriptions of reality contradict each other. Quantum mechanics governs the very small. It tells us that particles behave like waves, that uncertainty is unavoidable, that energy comes in discrete packets. General relativity governs the very large. It describes gravity as the curvature of spacetime, smooth and continuous, shaped by mass and energy. Each theory works astonishingly well in its own domain, but at the Planck length, both must apply at once, and when they do, the equations stop agreeing. If you try to measure a region of space smaller than the Planck length, you must use extremely high energy. That energy, according to general relativity, curves spacetime. Concentrate enough of it into a tiny region, and spacetime collapses into a black hole. The act of measurement destroys the very region you are trying to observe. This is not a practical inconvenience, it is a logical boundary. Space resists being examined beyond this point. It is as if the universe is saying, quietly but firmly, that the question itself has lost meaning. At scales larger than the Planck length, spacetime behaves like a smooth fabric. Distances can be measured, coordinates make sense. You can point to a location and say, here. But as you approach the Planck scale, that fabric begins to fluctuate. Quantum uncertainty causes spacetime itself to jitter. Physicist John Wheeler once described this as quantum foam, a restless sea of microscopic fluctuations, where tiny regions of spacetime bubble into and out of existence. In this picture, space is no longer a calm stage. It is alive with motion, constantly reshaping itself at the smallest scales. Time, too, becomes unstable. At the Planck time, about 5.4 to 1044 seconds, the concept of a smooth flow of moments breaks down. Events no longer occur in a well-defined sequence. Cause and effect blur. Before and after lose their usual meaning. This is deeply unsettling if you are used to thinking of space and time as continuous, but it may also be deeply revealing. It suggests that space-time itself is not fundamental, that it emerges from something deeper, something we do not yet fully understand. Several theories attempt to describe this deeper layer. Loop quantum gravity proposes that space is made of tiny, discrete loops woven together into a network. String theory suggests that the fundamental entities are not points at all, but vibrating strings existing in higher dimensions. In both cases, the smooth space we experience is an approximation, not the underlying truth. None of these ideas has yet been confirmed experimentally, and that too is part of the story. To probe the Planck length directly would require energies far beyond anything we can achieve. Even a particle accelerator the size of our galaxy would fall short. Nature has placed this boundary far beyond our reach. But limits are not failures, they are guides. The Planck length tells us where our current theories stop working. It marks the frontier where new physics must begin. And there is something quietly comforting about that. A reminder that reality is not obligated to be fully transparent. That mystery is not a flaw, but a feature. As you lie still, consider how rarely you encounter true limits in everyday life. You can always imagine something smaller, a finer grain, a sharper boundary. But here, the universe draws a line, not with force, but with subtlety. Beyond this point, the language we use to describe the world no longer applies. This does not mean that nothing exists below the Planck length. It means that below may no longer be a meaningful concept. Just as north of the North Pole does not exist, smaller than the Planck length may not correspond to any physical reality we can define. The smallest length is not a smallest object. It is a smallest distinction, a resolution beyond which separation itself dissolves, and this has profound implications. If space-time is quantized, then the universe has a built-in graininess, not in matter alone but in geometry. Space would not be infinitely divisible, time would not flow infinitely smoothly. Reality would be composed of finite units stitched together into the continuum we perceive. This graininess could help explain some of the deepest puzzles in physics: the origin of black hole entropy, the nature of the Big Bang, the unification of forces. The Planck scale is where these mysteries converge. It is also where humility enters science most clearly. We can calculate the Planck length, we can describe why it matters, but we cannot see it, we cannot measure it directly. We infer its existence from the consistency of our theories and the structure of the equations that describe nature. And that is enough for now. In a universe filled with vast distances and immense energies, it may seem strange that the smallest scales are the most elusive. But perhaps this is fitting. Perhaps the universe protects both its largest and smallest truths with the same quiet grace. The Planck length is not an obstacle to be overcome. It is a boundary to be respected, a reminder that knowledge has edges just like space does. And as we continue this calm descent into the foundations of reality, another question gently emerges. If space itself cannot be divided beyond a certain point, what happens when we pour energy into that smallest region and push nature toward collapse itself? Part 5. Energy that collapses reality. To see smaller details, you must use more energy. But push this too far, and the act of observation destroys what you are trying to see. At extreme concentrations, energy curves space-time into a black hole, hiding information behind a horizon. The universe enforces its limits gently but firmly. At first, the relationship between energy and vision feels straightforward. To see fine details, you need shorter wavelengths. Shorter wavelengths require higher energy. This principle has guided science for generations. Optical microscopes gave way to electron microscopes. Particle accelerators replaced lenses altogether, using collisions to reveal the hidden architecture of matter. Each advance followed the same quiet rule. If you want to look deeper, you must strike harder. But energy is never just energy. According to Einstein, energy and mass are interchangeable, and both shape space-time. When energy is spread out, its gravitational effect is negligible. When it is concentrated into a small region, space-time begins to bend. At low energies, this curvature is imperceptible. At high energies, it becomes decisive. Imagine focusing more and more energy into an ever smaller volume, hoping to probe finer details. Quantum mechanics allows this, at least in principle, but general relativity responds in kind. As energy density rises, space-time curves more sharply. Eventually, the curvature becomes so extreme that the region collapses inward, sealing itself off from the rest of the universe. A black hole is born. This is not science fiction. It is a direct consequence of well-tested equations. If enough energy is packed into a region smaller than its Schwarzschild radius, no force can prevent collapse. Not electromagnetism, not nuclear forces, not even quantum pressure. Gravity wins. At this point, the act of observation defeats itself. The region you were trying to study disappears behind an event horizon, a boundary beyond which information cannot escape. Light cannot return, signals cannot emerge. The universe does not explode or protest, it simply closes the door. This creates a profound limit on knowledge. No matter how advanced our technology becomes, there is a threshold beyond which seeing more requires destroying what is being seen. The universe allows exploration, but not intrusion without consequence. This limit is not just theoretical. Physicists can calculate the energy required to probe smaller and smaller scales. As the target size approaches the Planck length, the required energy approaches the Planck energy, around 1019 giga-electron volts. At that scale, the gravitational effects of the energy itself become unavoidable. Any attempt to probe beyond that would create a microscopic black hole. The measurement apparatus would collapse into the phenomenon it was trying to observe. In this way, black holes act as cosmic censorship. They prevent certain questions from being asked in physical terms. They hide regions where our concepts break down, preserving the consistency of the rest of spacetime. This is not a punishment, it is a safeguard. Black holes are often imagined as violent or destructive, but from this perspective, they are quiet enforcers of balance. They ensure that energy cannot be localized arbitrarily without reshaping reality. They remind us that spacetime is not an inert backdrop, but an active participant in every experiment. Even at astronomical scales, this principle holds. Stars form when gravity overcomes pressure. As mass increases, the star's core compresses, heating up and igniting nuclear fusion. There's a balance between outward pressure and inward pull. But if the mass becomes too great, pressure can no longer resist collapse. The star's core falls inward, forming a neutron star or a black hole. In each case, there is a limit. White dwarfs cannot exceed the Chandrasekhar limit. Neutron stars cannot exceed the Tolman-Oppenheimer-Volkoff limit. Beyond those thresholds, collapse is inevitable. Nature enforces stability only within defined boundaries. At the smallest scales, the same logic applies. Concentrate too much energy, and spacetime responds decisively. This has implications far beyond black holes themselves. It suggests that the universe has a built-in maximum resolution, a point beyond which reality refuses to be sharply defined, not because it is fuzzy, but because attempting to sharpen it further changes the object itself. This challenges the classical idea that observation can be made arbitrarily gentle. In quantum mechanics, observation already alters what is observed. At extreme energies, observation becomes creation or destruction. Some physicists have speculated that microscopic black holes might briefly form in high-energy particle collisions, evaporating almost instantly through Hawking radiation. If such events occur, they would last less than a trillionth of a second, leaving only subtle signatures behind. Even then, they would mark the edge of what is physically accessible. Stephen Hawking showed that black holes are not entirely black. Quantum effects allow them to emit radiation, slowly losing mass over immense timescales. This process hints that information may not be completely lost, but transformed in ways we do not yet fully understand. This leads to one of the deepest puzzles in modern physics, the black hole information paradox. If information falls into a black hole and the black hole eventually evaporates, what happens to the information? Is it destroyed or encoded in the radiation in some subtle way? The answer is still unfolding. But the question itself arises because of this fundamental limit, because the universe allows regions where information is hidden but not necessarily erased. As you lie quietly, it may be comforting to think of these limits not as walls but as contours. The universe has shape, it curves, it bends, it responds. It does not permit infinite intensity without consequence. This principle appears everywhere once you learn to see it. In material science, too much stress causes fracture. In biology, too much energy damages cells. In ecosystems, too much growth leads to collapse. Balance is preserved through limits. At cosmic scales, black holes are the expression of this balance. They form where energy and mass exceed what spacetime can support in open form. They are the universe's way of containing excess. And yet, even black holes are not eternal. Over timescales vastly longer than the current age of the universe, they fade. Energy returns to space in softened form. Horizons shrink. The universe continues its quiet evolution. So when we say that energy collapses reality, we are not describing an end. We are describing a transformation, a folding inward, followed by a gradual release, a reminder that extremes are temporary, but limits are enduring. The universe does not forbid curiosity. It simply guides it. It allows exploration up to the point where exploration itself would unravel the structure it depends on. And as we continue this gentle journey along the boundaries of what can be known, another question waits just beyond the horizon. If black holes hide information so completely, what does that mean for the universe's memory itself? And can anything ever truly be lost? Part 6. Why information cannot escape forever. Black holes are not just massive, they are boundaries. Once crossed, information cannot return, at least not in any classical sense. This creates one of the deepest puzzles in physics, whether the universe ever truly forgets anything, or whether all information is preserved in ways we cannot yet perceive. At first glance, a black hole appears simple, a region of space where gravity is so intense that nothing escapes. Not light, not matter, not signals of any kind. But beneath this simplicity lies a profound question that reaches into the foundations of reality itself. What happens to information when it disappears beyond that boundary? In physics, information is not abstract. It is the complete description of a system's state, the positions and motions of particles, their energies, charges, and quantum properties. If you knew all of this perfectly, the laws of physics would, in principle, allow you to predict the future and reconstruct the past. Information is what makes the universe intelligible. For most of physics, information is never destroyed. In classical mechanics, trajectories can be reversed. In quantum mechanics, the equations preserve information exactly. Even chaotic systems, while unpredictable in practice, still conserve information in theory. This principle is so deeply ingrained that many physicists treat it as inviolable. Black holes seem to challenge this. Imagine an object falling toward a black hole. As it approaches the event horizon, it appears to slow down from the perspective of a distant observer. Its light becomes redder, fainter. Time stretches. Eventually, it fades from view entirely. From the outside, the object never quite crosses the horizon. From its own perspective, however, it does. And once it does, there is no return. Everything that made that object what it was, its structure, its history, its information, now lies behind the horizon. Classical physics says that information cannot escape. If the black hole lasts forever, the information is effectively gone from the observable universe. This is where the puzzle begins. In the 1970s, Stephen Hawking made a discovery that complicated the picture. Using quantum field theory and curved spacetime, he showed that black holes are not perfectly black. They emit radiation. Slowly, steadily, they lose mass. Over unimaginably long timescales, they evaporate completely. This radiation, now called Hawking radiation, appears thermal, random, featureless. It carries energy but no obvious information about what fell in. If a black hole evaporates entirely, leaving only this radiation behind, where did the information go? If it is destroyed, then one of the core principles of quantum mechanics is violated. If it is preserved, then it must be encoded somehow in the radiation, or stored at the horizon, or hidden in a way we do not yet understand. This tension is known as the Black hole information paradox. It is not a technical curiosity. It strikes at the heart of whether the universe is fundamentally reversible or whether it allows true erasure. One possibility is that information is lost, that black holes really do erase it. This would mean that the universe is not fully deterministic at the deepest level, that some details of the past are truly gone, not just hidden. For many physicists, this is deeply unsettling. Another possibility is that information is preserved, but scrambled beyond recognition. In this view, the information is not destroyed, but transformed into an almost impossibly complex pattern spread across the Hawking radiation. Recovering it would require reconstructing correlations so subtle that they are effectively unreachable. A third idea suggests that information is stored on the event horizon itself. This led to the holographic principle, the idea that all the information contained in a volume of space can be described by data encoded on its boundary. In this picture, the black hole's surface carries a complete record of everything that has fallen in. This idea has gained remarkable support. In certain theoretical models, particularly in string theory, black holes behave in ways that preserve information exactly. Calculations show that the number of possible internal states of a black hole matches the information content suggested by its surface area, not its volume. This hints at something extraordinary, that the universe itself may be holographic, that the three-dimensional world you experience could be encoded on distant boundaries in ways we do not yet fully grasp. If this is true, then black holes are not destroyers of information, but extreme compressors. They take rich internal detail and encode it on a surface of finite size. Information is not lost, it is rearranged. Yet even this elegant solution leaves open questions. How does the information get out during evaporation? How is it encoded in radiation that looks random? How does causality remain intact? These questions are still being explored. But one thing has become clear. Black holes force us to confront the limits of what we mean by knowing something. As you lie quietly, it may help to think of information not as a fragile thing, easily erased, but as something deeply woven into the universe's structure. Patterns may be hidden, correlations may be spread thin, but complete erasure may be forbidden. This resonates with a deeper intuition that the universe remembers, that every interaction leaves a trace, even if it becomes inaccessible, that nothing truly vanishes without a record. And yet, from our perspective, black holes are perfect silencers. Once information crosses the horizon, it is gone from us. We cannot retrieve it. We cannot observe it. For all practical purposes, it no longer exists. This distinction matters. Physics often distinguishes between what is fundamentally true and what is operationally accessible. Even if information is preserved in some abstract sense, it may be forever beyond our reach. The universe may remember, even if we cannot. In that sense, black holes represent the ultimate boundary of observation, not just of space, but of knowledge. They define the limits of what any observer can ever hope to reconstruct. And there's something strangely peaceful about that. A reminder that not everything must be known, that mystery can coexist with understanding, that limits do not diminish reality, but shape it. The event horizon is not just a gravitational boundary, it is an epistemic one, a line beyond which questions lose their physical meaning for those outside. Black holes teach us humility. They show that even with our most powerful theories, there are regions where our language falters, where concepts like inside and outside, past and future, information and loss blur together. And yet, they also inspire progress. The information paradox has driven decades of insight into quantum gravity, space-time geometry, and the nature of reality itself. By confronting what seems impossible, physics has been forced to grow. Perhaps this is the universe's way of guiding inquiry, by placing boundaries not as dead ends, but as invitations to rethink what we assume. As the black hole evaporates, slowly returning energy to space, it may be whispering something profound, that nothing is ever truly isolated, that even the darkest regions are connected, however subtly, to the rest of the cosmos. And as we continue this quiet journey along the universe's limits, another question emerges naturally from the darkness. If information may never truly be lost, why then does time itself seem to move in only one direction, carrying memories with it, but never allowing them to return? Part 7. Time's One Way. Boundary. Time appears to flow in only one direction. We remember the past, never the future. This arrow of time is not imposed by clocks, but by entropy, the gradual spreading of energy. It is a limit not on motion, but on reversal, quietly shaping every experience you've ever had. As you lie here, breathing slowly, notice how natural this feels. One moment follows another. Thoughts arise, then fade. The room grows quieter. Nothing in your experience suggests that time could flow the other way. And yet, when physicists write down the fundamental equations that govern motion, almost all of them work just as well backward as forward. If you reverse the direction of time in those equations, they would still hold. This creates a gentle but profound tension. The laws of physics are mostly time-symmetric, but your life is not. A glass can fall and shatter, but it never reassembles itself. Smoke spreads through a room, but it never gathers back into a cigarette. You grow older, never younger. Somewhere between equations and experience, direction appears. That direction is entropy. Entropy is often described as disorder, but this is only a shadow of its true meaning. More precisely, entropy measures how many microscopic arrangements correspond to the same macroscopic state. A neat stack of papers has very few possible arrangements. The same papers scattered across the floor have vastly more. Nature tends to move from fewer possibilities to more. This tendency is not driven by intention or force. It is statistical. Given enough particles and enough time, the most likely outcome is the one with the greatest number of possible configurations. Energy spreads out, gradients smooth, differences fade. This is the arrow of time. When heat flows from hot to cold, it is not because it cannot flow the other way in principle. It is because there are overwhelmingly more ways for energy to be spread out than concentrated. The reverse process is so unlikely that it never happens in practice. Every memory you have is a record of entropy increasing. Your brain stores information by creating physical changes, chemical gradients, electrical patterns that require energy. Recording the past produces heat. Remembering the future would require entropy to decrease, and the universe simply does not allow that on macroscopic scales. Even the act of observation is asymmetric. Light enters your eyes, signals move inward, information accumulates. Nothing about this process can be undone without leaving traces behind. This asymmetry does not come from clocks. Clocks merely measure time's passage. They do not create its direction. The arrow of time exists even in the absence of any device to track it. It is written into the behavior of matter itself. But this raises a deeper question. Why was entropy low in the past? If entropy always increases, then earlier times must have been more ordered than later ones. The universe, at some point, must have started in a remarkably low entropy state, and indeed, observations confirm this. The early universe was extraordinarily smooth, uniform, and ordered. This initial condition is one of the deepest mysteries in cosmology. The laws of physics do not demand such order. They permit countless other beginnings, yet our universe began in a state of astonishing simplicity. From that simplicity, complexity emerged. As the universe expanded and cooled, tiny fluctuations grew. Gravity amplified differences, stars formed, galaxies assembled, entropy increased even as structure appeared. This may seem paradoxical, but it is not. Local order can arise as long as total entropy increases overall. Life itself is an entropy machine. Living systems maintain internal order by exporting disorder to their surroundings. Every heartbeat, every breath, every thought increases entropy somewhere else. Life does not defy the arrow of time, it rides it. As you rest, your body continues this process quietly. Heat dissipates, molecules diffuse, cells repair themselves using stored energy. All of it moves in one direction only. At the smallest scales, the picture becomes more subtle. In quantum mechanics, individual processes can be time reversible. A particle interaction can run forward or backward with equal probability. But when many such processes combine, statistical behavior emerges. Entropy reasserts itself. Time's arrow is not built into the smallest laws. It emerges when many degrees of freedom interact. It is a collective phenomenon, arising from numbers too large to reverse. This is why time feels so relentless, not because the universe is forcing it forward, but because reversing it would require coordinating unimaginable amounts of information. Every particle would have to retrace its path perfectly. Every vibration would need to unwind. The probability of this happening spontaneously is so small that it may as well be zero. Black holes deepen this story. They have enormous entropy, proportional to the area of their event horizons. When matter falls in, entropy increases dramatically. When black holes evaporate, entropy increases again. Even the most extreme objects in the universe obey the arrow of time. The universe itself appears to be moving toward a state of maximum entropy, a future sometimes called heat death. In that distant era, energy differences will be minimal. Stars will fade, structures will dissolve, time will still pass, but little will change. This is not an ending in the dramatic sense. It is a settling, a quiet leveling of contrasts. And yet, within this long arc, moments matter, because time's arrow gives them order. It allows causes to precede effects. It allows learning. It allows growth. Without this asymmetry, experience itself would unravel. Imagine a universe with no arrow of time. Events would not form sequences. Memory would be impossible. Consciousness would have no flow. There would be no stories, no anticipation, no rest. The one-way nature of time is not a flaw. It is what makes existence coherent. Some physicists have wondered whether the arrow of time could reverse in other regions of the universe or under exotic conditions. So far, all evidence suggests that while local fluctuations can occur, the overall direction remains the same. Entropy increases globally. Even the expansion of the universe may be tied to this arrow. As space grows, new room for entropy opens up. More ways for energy to spread, more configurations become possible. Time and expansion may be quietly linked. As you listen, the past is fixed. The future is open. This openness is not absolute freedom, but possibility shaped by laws. The arrow of time ensures that choices have consequences, that actions matter because they cannot be undone. There is something deeply calming in accepting this. You do not need to rewind, you do not need to reverse. You move forward, as everything does, carried by a universe that knows only one direction. Time's boundary is not a wall you hit. It is a current you drift with. You cannot swim against it, but you can float, steady and aware. And as we continue this gentle journey through the universe's limits, another question begins to form. If time has a direction and entropy defines its flow, is there also a maximum temperature, a limit to how intense energy itself can become before the universe changes its rules once again? Part 8. The maximum possible temperature. There may be a hottest temperature the universe allows. At extreme energies, particles collide so violently that adding more heat no longer increases temperature in the usual way. Instead, new forms of matter appear, hinting at a thermal ceiling built into physics itself. Temperature feels familiar. It is the warmth of sunlight on your skin, the quiet cooling of a room at night, the gentle balance your body maintains as you rest. We learn early that temperature rises when something is heated and falls when it cools. It feels continuous, open-ended, as though you could always add more heat and push it higher. But in the deepest reaches of physics, this intuition begins to soften. Temperature is not an independent substance, it is a measure of motion. Specifically, it reflects the average kinetic energy of particles, their restless vibration, their collisions, their ceaseless motion through space. At everyday scales, adding energy increases motion. Molecules move faster, atoms vibrate more intensely, temperature rises. But as we climb higher and higher on the energy scale, something unexpected happens. Motion no longer tells the whole story. As particles approach extreme energies, collisions stop behaving like simple impacts. Instead of merely bouncing faster, particles begin to transform. Energy condenses into mass. New particles appear. Degrees of freedom multiply. The added energy is no longer expressed as higher temperature, but as new forms of matter. This is the first hint that temperature may have an upper limit. In the early universe, temperatures were unimaginably high. In the first fractions of a second after the Big Bang, energy densities were so extreme that matter as we know it could not exist. Quarks and gluons moved freely in a dense plasma. Forces that are now distinct were once unified. Space itself was compressed beyond anything we can recreate today. As the universe expanded, it cooled. Temperature fell, not because energy disappeared, but because it spread out. Expansion created room. Motion diluted. New structures became possible. Physicists can trace this cooling backward, estimating temperatures at earlier and earlier times. As they do, they encounter natural thresholds. At certain energies, phase transitions occur. Protons and neutrons form. Atoms appear. Light decouples from matter. Each transition marks a change in how energy is organized. But above all of these lies a more profound boundary, a temperature so high that the concept itself begins to lose meaning. This is often associated with the Planck temperature, around 1.4 x 1032 Kelvin, a number so large it defies comparison. At this temperature, the average energy of particles is comparable to the energy required to create black holes at microscopic scales. Quantum gravity effects dominate. Space-time fluctuations become unavoidable. At this point, temperature as we understand it ceases to function as a useful concept. Adding energy no longer simply increases motion, it changes the structure of reality itself. This is not just speculation. Particle physics offers gentler previews of this behavior. In high-energy collisions, such as those produced in particle accelerators, adding energy eventually stops increasing temperature in the expected way. Instead, energy goes into producing heavier particles, new states, and more complex interactions. One striking example is the Hagedorn temperature, a concept that arose in the study of strongly interacting particles. Beyond a certain point, adding energy creates more particles rather than increasing thermal motion. Temperature plateaus. The system absorbs energy by becoming more complex, not hotter. This behavior suggests that temperature is not infinitely extensible. It is constrained by the available ways energy can be expressed. At extreme densities, particles are no longer independent. They merge into collective states. Quark-gluon plasma behaves less like a gas and more like a nearly perfect fluid. Motion becomes correlated. Temperature loses its simple interpretation. And beyond that, at energies approaching the Planck scale, space-time itself participates. Energy curves geometry so strongly that any attempt to define a local temperature becomes ambiguous. The region collapses, hides itself, or fluctuates beyond classical description. The universe does not allow unlimited thermal intensity in open form. It redirects excess energy into new dimensions of behavior. This thermal ceiling is not imposed arbitrarily. It emerges from the same principles that govern black holes, space-time curvature, and quantum uncertainty. Energy cannot be concentrated arbitrarily without consequence. At some point, the system reorganizes. You can think of this as a kind of safety valve. Instead of letting temperature rise without bound, the universe changes phase. It introduces new particles, new symmetries, new geometry. In this sense, the hottest temperatures are not merely dangerous, they are transformative. This has deep implications for cosmology. The early universe did not begin in a state of infinite temperature. Although often described that way in simplified language, the true picture is more subtle. Our equations point toward a regime where temperature stops being well-defined, not one where it diverges to infinity. The Big Bang was not an explosion into space, but an expansion of space itself from an extremely hot, dense state. As we extrapolate backward, we do not reach infinite heat. We reach a boundary where our descriptions fail. That boundary is not a singular value to be crossed, but a regime to be understood. As you rest here, it may be comforting to know that even extremes have limits, that the universe does not permit unbounded intensity, that it protects itself from runaway conditions by changing the rules. This pattern appears everywhere. In stars, nuclear fusion balances gravity until fuel runs out. In planets, pressure and temperature settle into equilibrium. In life, chemical reactions proceed within narrow thermal ranges. Too cold and motion stops. Too hot and structure dissolves. At cosmic scales, the same principle applies. There is a window where structure can exist, bounded on both ends by limits of temperature and density. The maximum possible temperature marks one edge of that window. Beyond it, the universe does not burn hotter, it becomes something else entirely. Physicists are still working to understand what that something else is. Theories of quantum gravity aim to describe this regime, where spacetime, matter, and energy are inseparable, where temperature, length, and time blur together. We may never be able to test these ideas directly. The energies involved are far beyond any experiment we can perform. But indirect clues continue to accumulate, guiding theory gently forward. And perhaps that is enough. Not every boundary must be crossed to be meaningful. Some exist to define the shape of possibility itself. As the universe cooled from its earliest moments, it passed through this thermal ceiling quietly, without drama. New forms of matter emerged, forces separated, structure became possible. The existence of stars, planets, and life depends on this cooling path. The fact that there is a maximum meaningful temperature is not a limitation on existence. It is what makes existence stable. As you breathe, your body maintains its own narrow thermal balance. A few degrees higher or lower, and processes falter. Life thrives within limits. So does the universe. And as we continue this calm exploration of cosmic boundaries, another question begins to take shape. If temperature has a ceiling and energy reorganizes itself rather than rising forever, what does that say about certainty itself? And are there limits not just to heat, but to what can ever be known at all? Part 9. The limit of perfect knowledge. Quantum mechanics places a boundary on certainty. No matter how carefully you measure, some pairs of properties can never be known at the same time. This is not a flaw in instruments. It's a rule of reality. Precision has a cost, and the universe collects it every time. At first, this feels counterintuitive. In everyday life, knowledge seems additive. Measure something more carefully, and uncertainty shrinks. Use a better ruler, a sharper lens, a more precise clock, and the world reveals itself more clearly. For centuries, this belief guided science. The universe was thought to be knowable in principle, even if difficult in practice. Quantum mechanics quietly changed that assumption. At the smallest scales, nature does not reward unlimited precision. Instead, it imposes a trade-off. The more precisely you know one aspect of a system, the less precisely you can know another. This is not because of human error or imperfect tools. It is because those aspects do not simultaneously exist in a sharply defined way. The most famous expression of this limit is the Heisenberg uncertainty principle. It states that you cannot know both the position and the momentum of a particle with arbitrary precision at the same time. The product of their uncertainties has a minimum value. Reduce one, and the other must grow. This is often misunderstood as a statement about disturbance, as if measuring position kicks the particle and changes its momentum. While measurement can disturb a system, the deeper truth is more subtle. Even before you measure, the particle does not possess exact values of both quantities simultaneously. The uncertainty is intrinsic. Particles are not tiny billiard balls following precise trajectories. They are described by wave functions, mathematical objects that encode probabilities. These probabilities are not placeholders for ignorance. They are the most complete description the universe allows. When you ask where a particle is, you are asking the universe to choose from among possibilities. When you ask how fast it is moving, you are asking a different question. The universe can answer one clearly, but not both at once. This limit extends far beyond position and momentum, energy and time. Different components of angular momentum, particle number, and phase, each pair carries its own uncertainty relationship. Each represents a boundary on simultaneous knowledge. What makes this so profound is that these limits are not negotiable. No clever experimental design can evade them. No future technology will overcome them. They are written into the structure of quantum theory itself. And yet, the universe remains astonishingly predictable. Quantum mechanics does not forbid knowledge, it reshapes it. Instead of exact values, it offers probabilities that evolve with precise mathematical rules. The wave function obeys deterministic equations. What is uncertain is not the evolution of the wave function, but the outcome of specific measurements. This is a subtle but important distinction. The universe is lawful, but not fully determinate in the classical sense. It does not commit to specific outcomes until interaction occurs. This brings us to one of the most unsettling aspects of quantum theory. Measurement is not passive, it is participatory. When you measure a system, you do not simply reveal a pre-existing fact. You help bring one possibility into reality. This does not mean consciousness controls reality in a mystical sense. It means interaction matters. Any measurement is an interaction, and interactions change the system being measured. At macroscopic scales, these effects average out. Objects have well-defined positions and velocities. Uncertainty becomes negligible. Classical physics emerges naturally, but at the quantum level, the limits remain unavoidable. These limits have been tested with extraordinary precision. Experiments using photons, electrons, and even large molecules confirm the uncertainty principle again and again. Violations are not merely unobserved. They are mathematically forbidden. This boundary on knowledge has deep consequences. It means the universe does not allow complete specification of its state in classical terms. There is no hidden ledger containing exact values for everything at all times waiting to be read. Some interpretations of quantum mechanics once hoped for hidden variables, unknown parameters that restore certainty beneath the surface. Decades of experiments, particularly tests of Bell's inequalities, have shown that any such hidden variables must behave in ways that defy locality or realism. Nature does not allow simple completion. Instead, the universe seems comfortable with ambiguity. This ambiguity is not chaos. It is structured uncertainty, a kind of softness built into reality, preventing it from becoming rigidly overdetermined. As you lie here, notice how this mirrors experience. You never know everything about a situation. Some clarity comes at the expense of other details. Focus sharpens one aspect while blurring another. Awareness itself has limits. Quantum mechanics formalizes this intuition at the deepest level. It also places a limit on prediction. Even with perfect knowledge of a wave function, you cannot predict the exact outcome of a single measurement. You can only assign probabilities. The universe refuses to be fully forecast. And yet, these probabilities are extraordinarily reliable. Quantum theory predicts outcomes with accuracy unmatched by any other physical theory. Lasers, semiconductors, atomic clocks, and medical imaging all rely on these principles. The limits on knowledge do not weaken science, they enable it. There is a quiet elegance here. The universe balances determinism and freedom, law and openness, structure and surprise. This balance may be essential. If everything were perfectly knowable, the universe would be frozen in predictability. If everything were random, coherence would dissolve. The quantum world sits gently between these extremes. The limit of perfect knowledge also protects reality from paradox. It prevents infinite precision, infinite information density, infinite control. It ensures that observers are part of the systems they observe, not detached masters standing outside. This becomes especially important when combined with earlier limits we've explored. The speed of light restricts information flow. Horizons restrict access. Entropy restricts reversal. The uncertainty principle restricts specification. Together, they define a universe that is rich, dynamic, and stable. Even black holes reflect this limit. The information paradox arises because quantum mechanics insists that information cannot be destroyed, while classical gravity seems to hide it completely. Resolving this tension requires respecting the limits on knowledge imposed by both theories. In modern physics, these ideas converge on a humbling realization. The universe is not a puzzle with all pieces visible at once. It is a process that reveals itself gradually, selectively, and never in full. As you breathe, the world around you feels solid and definite, and at your scale, it is. But beneath that solidity lies a realm where certainty softens, where possibilities coexist, where knowledge has edges. These edges are not failures of understanding, they are features of existence. The limit of perfect knowledge does not mean we know nothing. It means we know in a particular way, probabilistically, contextually, relationally. This has philosophical weight, but it also has emotional resonance. It suggests that uncertainty is not an enemy of meaning, it is part of it, that openness is woven into reality itself. As we continue this quiet journey, another boundary waits ahead, shaped not by uncertainty, but by gravity's most extreme expression. If knowledge has limits and information can be hidden, what happens at the deepest interior of a black hole, where even time and space exchange roles and the idea of after may no longer apply? Part 10. The Horizon. Inside. Black holes. Beyond a black hole's event horizon, the idea of after breaks down. Time and space exchange roles, and all possible futures point inward. This is not just a dangerous place. It's a region where the structure of reality enforces a final direction. From the outside, a black hole feels like an object, massive, compact, defined by a boundary in space. But this impression is deceptive. A black hole is not merely something you approach. It is something you enter into a different ordering of reality, where familiar ideas, distance, duration, direction, quietly unravel. The event horizon is not a surface you strike or a wall you collide with. If you were falling toward it, you would notice nothing special at the moment you crossed. No jolt, no flash. Locally, the laws of physics remain calm. Your heartbeat continues. Your thoughts remain intact. And yet, once crossed, the universe has already changed in a way that cannot be undone. Outside the horizon, space is something you move through, and time is something that moves you forward. Inside, these roles begin to exchange. The inward direction toward the center of the black hole becomes as inevitable as the passage of time. Just as you cannot stop tomorrow from arriving, you cannot stop moving inward once you are inside. This is not poetry. It is geometry. In Einstein's description of gravity, space-time curves in response to mass and energy. Near a black hole, that curvature becomes extreme. The light cones, the structures that define what directions light, and therefore causality, can take, tilt inward. All future directed paths lead toward the center. Outside the horizon, you still have choices. You can move forward or backward, left or right. Inside, choice collapses. Every possible future points the same way. This is what it means to say that the horizon enforces a final direction. The idea of after depends on the ability to remain where you are while time passes. Inside a black hole, remaining where you are is no longer an option. The inward direction is not a place, it is a moment, a progression. Falling inward is not something that happens over time, it is time. To an external observer, clocks near the horizon appear to slow down, their ticks stretching farther apart. Signals grow weaker, redshifted, fading toward silence. This creates the illusion that nothing ever crosses the horizon. But this is an illusion of perspective. For the falling observer, time continues normally. The crossing happens in finite time. The separation between viewpoints is absolute. This split in experience is one of the most unsettling features of black holes. Two observers can disagree about the order of events, not because one is mistaken, but because space-time itself allows different realities depending on position and motion. Inside the horizon, the disagreement deepens. There, the central singularity, whatever it truly is, lies not ahead in space but ahead in time. You cannot avoid it any more than you can avoid the next second arriving. You can delay it slightly, but you cannot turn away. The structure of space-time forbids it. This gives black holes a strange intimacy with time. They are not merely regions of strong gravity. They are regions where time itself becomes directional in an absolute sense. And yet, even here, our understanding is incomplete. The classical picture predicts a singularity, a point where density becomes infinite, curvature diverges, and the equations of general relativity cease to make sense. But physicists widely believe this is not the end of the story. Singularities likely signal the breakdown of the theory, not the breakdown of reality. Quantum effects are expected to intervene before true infinities arise. Just as the Planck length limits how small distances can become, something may limit how extreme curvature can grow. Inside a black hole, spacetime may transition into a new phase, one we do not yet know how to describe. Some theories suggest that the interior may connect to other regions of spacetime. Others propose that the singularity is replaced by a dense but finite core. Still others imagine that black holes give birth to new expanding regions, universes budding from collapse. These ideas remain speculative. What is not speculative is the role of the horizon as a one-way boundary. Once crossed, the external universe is forever inaccessible. Light cannot escape. Signals cannot return. Causality itself is redirected inward. This makes the horizon a deeper boundary than any we have encountered so far. Not just a limit on motion or knowledge, but a limit on narrative. Stories that pass beyond it cannot be continued from the outside. In this sense, black holes are the universe's most decisive punctuation marks. As you rest, consider how different this is from everyday danger. Fire burns, but you can step away. Heights frighten, but you can climb down. Even the speed of light is a limit you approach asymptotically. The horizon, by contrast, is absolute. Cross it, and the grammar of reality changes. And yet, the crossing itself is gentle. This is another quiet lesson of physics. The most profound boundaries are often the least dramatic. They announce themselves not with spectacle, but with inevitability. The horizon does not shout. It simply exists. Black holes also teach us something subtle about determinism. Inside the horizon, the future is fixed in a way that feels unfamiliar. Outside, the universe allows branching possibilities. Inside, the branching collapses into a single inward path. This does not mean the universe becomes simple. On the contrary, the interior may be extraordinarily complex, but the direction of evolution is constrained. The arrow of time and the direction of space align. This alignment echoes something deeper. Across the universe, limits often appear where freedom and structure must be balanced. Too much freedom and coherence dissolves. Too much structure and nothing can change. Black holes sit at this balance point, enforcing direction without prescribing detail. They are not violations of cosmic order, they are expressions of it. Even as black holes grow by consuming matter and energy, they obey simple laws. Their mass increases, their surface area grows, their entropy rises. These behaviors mirror thermodynamics, hinting that horizons are not just geometric features, but thermodynamic ones. This realization has reshaped theoretical physics. It suggests that spacetime itself may have microscopic degrees of freedom, that horizons carry entropy because they encode information. The interior and exterior are linked by deep, subtle rules we are only beginning to glimpse. In recent years, ideas like entanglement and holography have suggested that spacetime connectivity may arise from quantum correlations. In this view, the interior of a black hole is not separate from the exterior, but encoded within it in a highly non-local way. If this is true, then the horizon is not a severing of reality, but a reorganization. The information does not vanish, it is redistributed across scales and descriptions. Still, for any observer falling inward, these abstract resolutions offer little comfort. Experience ends in finite time. Futures converge. The universe enforces closure. There is something solemn about that, a reminder that not all journeys are open-ended, that some paths, once taken, have no return. But there is also something clarifying. Boundaries give shape to meaning. Without them, stories drift endlessly. With them, moments matter. Black holes are not enemies of the universe. They are part of its architecture. They regulate extremes. They test theories. They reveal where our language breaks and where new understanding must begin. As we move on from this boundary, another question naturally arises, softer but no less profound. If black holes enforce final directions and time itself can point inward, does the universe as a whole also face an ultimate ending? Or is there a larger boundary waiting far beyond even these darkest horizons? Part 11. Can the universe end? Even the universe may have a boundary in time. Whether it fades slowly into cold darkness, tears itself apart, or cycles into something new, cosmology suggests that expansion cannot remain unchanged forever. Every beginning carries the question of an ending. When you look up at the night sky, it feels timeless. Stars appear fixed. Constellations return year after year. The universe seems like a stage that has always been there and always will be. For most of human history, this intuition went unchallenged. The cosmos was eternal, unchanging, a steady backdrop against which life briefly unfolded. Modern cosmology gently dismantled that idea. We now know the universe has a history. It expanded from a hot, dense beginning roughly 13.8 billion years ago. Galaxies formed, stars ignited, space itself stretched. Time, as we experience it, began with this expansion, and once a beginning is admitted, an ending becomes a meaningful question. The universe is not static. It is evolving, and evolution, by its nature, invites limits. To ask whether the universe can end is not to ask whether everything suddenly stops. It is to ask how the large-scale behavior of spacetime changes over immense stretches of time. It is to ask whether expansion continues forever, slows, reverses, or transforms into something unrecognizable. Cosmologists explore these possibilities using observations and equations. They measure how fast galaxies recede. They study the cosmic microwave background. They examine how matter and energy are distributed. From this, they infer the universe's overall geometry and fate. One possible ending is quiet and gradual. Often called heat death, it is a future where the universe continues expanding indefinitely. Galaxies drift farther apart, stars burn out, black holes slowly evaporate, energy spreads thinner and thinner until no meaningful gradients remain. In this scenario, time does not stop, but change does. The universe approaches maximum entropy. Nothing dramatic happens. The cosmos simply settles into stillness. This outcome follows naturally from the second law of thermodynamics. If entropy continues to increase, eventually there will be no significant differences left to drive processes. No stars forming, no chemistry, no life. Just cold, dilute space filled with low-energy radiation. Another possibility is more violent. If dark energy grows stronger over time, the expansion of space could accelerate without bound. In this scenario, known as the Big Rip, galaxies are pulled apart, then star systems, then planets. Eventually, even atoms are torn asunder as space itself overwhelms all forces. Distances shrink in a strange way. The future arrives faster and faster. Structures dissolve not because they age, but because the fabric they rely on is stretched beyond cohesion. This outcome depends on the exact nature of dark energy, which remains one of the deepest mysteries in physics. Current observations suggest dark energy behaves like a constant, leading to gentle acceleration rather than runaway destruction. But uncertainty remains. A third possibility is more cyclical. In some models, expansion slows over time, eventually halting and reversing. The universe contracts, growing hotter and denser, culminating in a big crunch. This could be followed by another expansion, perhaps repeating the process. Such cyclic models are appealing because they avoid a final ending. They replace it with rhythm. But current data suggests the universe's expansion is accelerating, making a future contraction unlikely unless new physics intervenes. There are also more subtle ideas. The universe could tunnel into a different vacuum state, triggering a phase transition that reshapes the laws of physics themselves. This would not be an ending in the usual sense, but a transformation so complete that the universe as we know it would cease to exist. In this case, the end would not come as destruction, but as redefinition. What all these possibilities share is an acknowledgement that the universe is not immune to change. Its current state is not guaranteed forever. Expansion itself has a history. It began, evolved, and may one day alter its character. This realization can feel unsettling. We are used to thinking of endings as losses, but in cosmology, an ending is also a boundary of explanation. It defines the domain where our current models apply. Just as the speed of light limits motion and entropy limits reversal, cosmic endings limit duration. They tell us that time itself may have a shape. It is important to notice how distant these futures are, trillions upon trillions of years away, far beyond the lifespan of stars, far beyond the era when galaxies resemble anything familiar. These endings are not looming threats, they are asymptotic horizons. As you rest, there is no urgency here. The universe is not rushing toward its conclusion, it is unfolding at a pace so slow that human scales dissolve entirely. And yet, thinking about cosmic endings can bring a strange calm. It places everything in perspective. Worries shrink. Moments feel precious, not because they are fragile, but because they exist within a vast ordered flow. The universe does not end out of malice or neglect. It follows its laws to their natural conclusions. Whatever happens next will not be chaos. It will be structured by principles as consistent as those that shaped the past. There is also a deeper question beneath all of this. Does an ending imply finality, or does it simply mark the end of one phase? Physics has taught us to be cautious with absolutes. What looks like an end from one perspective often reveals itself as a transition from another. Atoms decay, but their energy persists. Stars die, but their elements seed new systems. Even black holes, once thought eternal, slowly fade. Perhaps the universe itself follows this pattern, not eternal in form, but persistent in transformation. Some theories suggest that our universe may be one of many, part of a larger structure where endings give rise to beginnings elsewhere. Others propose that time itself may not be fundamental, emerging from deeper relationships that do not require a start or finish. These ideas remain speculative, but they highlight something important. The question of whether the universe can end is inseparable from the question of what we mean by existence. From within the universe, endings feel absolute. From a broader view, they may be contextual. As you breathe, the present moment continues effortlessly. The universe does not demand that you resolve its ultimate fate. It simply invites you to notice that everything unfolds within boundaries, including time itself. Every beginning carries the question of an ending, but every ending also carries the quiet implication of continuity, of laws persisting, of patterns reshaping, of reality not disappearing, but changing its form. And as we continue this gentle exploration, another question naturally arises, closer to home. If the universe itself is governed by limits of stability and change, what keeps structures, from atoms to galaxies, from falling apart, long before any cosmic ending arrives at all? Part 12. The limit of stability. Too much mass in one place collapses. Too much energy disrupts structure. From stars to galaxies, balance is required for existence. These limits are why the universe forms patterns instead of chaos, and why everything you see holds together at all. At first glance, the universe appears full of extremes, vast emptiness punctuated by dense stars, violent explosions followed by long silence. And yet, beneath this contrast lies an extraordinary tendency toward balance. Nothing that exists does so arbitrarily. Every structure, from the smallest atom to the largest galaxy cluster, survives only by staying within narrow limits. Stability is not the absence of change, it is the careful negotiation between opposing forces. Consider a star. It exists because two powerful tendencies cancel each other out. Gravity pulls inward, compressing the star's mass toward its center. At the same time, nuclear fusion in the core releases energy outward, generating pressure that resists collapse. For millions or billions of years, these two forces remain in delicate equilibrium. If gravity wins, the star collapses. If pressure dominates, the star expands and sheds its outer layers. A star's life is defined by how long it can maintain this balance. Once its fuel runs low, equilibrium fails. The result may be a quiet cooling, a violent supernova, or the formation of a neutron star or black hole. In every case, collapse or disruption follows excess. This same principle governs planets. A planet must be massive enough for gravity to pull material together into a sphere, but not so massive that it ignites fusion and becomes a star. Too small, and it cannot hold an atmosphere. too large, and it crosses a threshold where its identity changes completely. Even the shape of a planet reflects limits. Rocky worlds can only grow so large before gravity overwhelms material strength. Beyond that point, gas dominates, structure reorganizes, categories shift. Galaxies, too, live at the edge of stability. Stars orbit within them, bound by gravity and guided by invisible halos of dark matter. Too little mass, and galaxies disperse. Too much concentration, and their cores collapse into supermassive black holes. The universe does not prevent extremes. It allows them, but only within structure. When mass or energy exceeds what a system can support, the system transforms. This transformation is not random. It follows predictable pathways dictated by physics. Excess mass becomes a black hole. Excess energy becomes radiation. Excess density becomes expansion or collapse. In this way, the universe avoids chaos not by suppressing extremes, but by channeling them. At smaller scales, the same logic applies. Atoms exist because electrons occupy stable energy levels around nuclei. If an electron had too little energy, it would spiral inward and collapse into the nucleus. Too much, and it would escape entirely. Only specific energy states are allowed. These quantized levels are another form of stability limit. Nature permits only those arrangements that can persist. Everything else dissolves. Even atomic nuclei obey this rule. Too many protons packed together create intense electrical repulsion. Only certain combinations of protons and neutrons remain stable. Others decay, transforming into different elements until balance is restored. This quiet insistence on stability is why the periodic table exists at all. Life depends on these limits. Chemistry depends on stable atoms. Biology depends on stable molecules. Cells depend on stable temperatures, pressures, and energy flows. Push any of these beyond their narrow windows, and structure fails. The universe does not support infinite variety. It supports survivable variety. This is not a restriction on creativity. It is what makes creativity meaningful. Patterns emerge because not everything is allowed. Forms repeat because stability selects them. Entropy plays a role here as well. While entropy tends to increase overall, local pockets of order can form where energy flows allow them to persist. Stars, planets, weather systems, and living organisms are all examples of order sustained by throughput, energy moving from concentrated sources to diffuse sinks. But this balance cannot last forever. When energy sources fade or limits are exceeded, structure dissolves. The universe reclaims its material and redistributes it. This is not destruction in a moral sense, it is recycling at cosmic scale. As you rest, your body is engaged in countless balancing acts. Blood pressure regulated, temperature maintained, chemical reactions tuned. None of these processes aim for perfection. They aim for survival within limits. Too much stress and systems fail, too little activity, and they weaken. Balance is dynamic, not static. This idea extends to spacetime itself. General relativity shows that mass and energy curve spacetime, but spacetime can only curve so much before it pinches off into horizons. Black holes represent the ultimate failure of structural balance, where gravity overwhelms all opposing forces. Even then, the universe does not allow unbounded collapse. Horizons form, singularities are hidden, information is constrained, limits assert themselves. This suggests something profound. Stability is not accidental, it is a principle. The universe appears finely tuned, not in the sense of intention, but in the sense of constraint. Only certain ranges of parameters allow complex structures to exist. If forces were slightly stronger or weaker, if particle masses were slightly different, stars might not form. Chemistry might fail, galaxies might never coalesce. This sensitivity has led some to speculate about deeper explanations. Selection effects, multiverses, underlying symmetries. Others see it simply as a fact of existence. The universe is as it is, because if it were otherwise, there would be nothing to observe it. Regardless of interpretation, the presence of stability limits is undeniable. They give the universe texture. Without them, matter would either collapse instantly or disperse endlessly. There would be no long-lived structures, no gradients to explore, no time for complexity to arise. Stability limits create longevity. They allow stars to shine steadily rather than explode immediately. They allow planets to orbit predictably rather than drift apart. They allow atoms to persist long enough for chemistry to matter. And they allow you to rest here now, supported by a world that holds together. The universe is not balanced perfectly. It is balanced sufficiently, enough to permit change without annihilation, enough to allow motion without disintegration. This is perhaps one of the quietest and most generous features of reality, that extremes are tempered, that boundaries exist, that not everything collapses or explodes at once. As we continue this gentle journey toward the edges of what can exist, another boundary comes into view, one that governs not structure, but influence itself. If stability requires balance and collapse follows excess, how far can any cause truly reach before the universe itself says, no farther? Part 13. The cosmic speed of causality. Events can only influence other events within strict boundaries. Causality itself travels at a limited speed, preventing instant effects across space. This keeps the universe coherent, local, and surprisingly calm, even across unimaginable distances. In everyday life, cause and effect feel immediate. You touch a surface and feel it instantly. You speak and hear your own voice without delay. The world seems tightly stitched together, responsive, connected. It's easy to forget that even these familiar interactions are governed by a finite speed, one so fast that its limits are hidden from perception. But on cosmic scales, those limits reveal themselves clearly. Nothing in the universe happens everywhere at once. Every cause spreads outward step by step, carried by signals that move no faster than light. This simple rule, so quiet it often goes unnoticed, is one of the deepest stabilizing principles of reality. Causality is not an abstract concept imposed by philosophy. It is a physical process bound to spacetime. When something happens, its influence propagates outward through fields and particles constrained by the geometry of the universe itself. This propagation defines what physicists call the light cone. For any event, there's a region of spacetime that can be affected by it, the future light cone, and a region that could have influenced it, the past light cone. Outside these cones, events are causally disconnected. They cannot affect one another, no matter how dramatic or energetic they may be. This structure ensures that the universe does not unravel. Imagine if causality were instantaneous. A fluctuation in one corner of the universe could immediately alter conditions everywhere else. Small disturbances would cascade uncontrollably. Structure would dissolve into chaos. Prediction would become impossible. The universe would have no coherence. Instead, causality moves at a finite pace. It gives the universe time to respond. It localizes effects. It allows complexity to emerge gradually rather than all at once. Even gravity obeys this rule. Although it once seemed instantaneous, we now know that changes in gravitational fields propagate at the speed of light. When massive objects move, they send ripples, gravitational waves, through spacetime. These waves travel outward, carrying information about the change. The detection of gravitational waves confirmed this beautifully. When two black holes collide, the distortion of spacetime reaches Earth not instantly, but after traveling for millions or billions of years. Cause follows effect, but only after crossing the intervening distance. This limit on causality is deeply tied to the structure of spacetime. According to relativity, space and time are not separate arenas. They form a unified fabric where the speed of light acts as a conversion factor between distance and duration. To exceed this speed would be to violate the geometry itself. As a result, causality is preserved. Effects do not precede causes. Information does not arrive before it is sent. Paradoxes are avoided not by clever rules, but by the universe's architecture. This becomes especially important when considering quantum phenomena. Quantum mechanics allows for strange correlations between distant particles, known as entanglement. Measuring one particle can instantaneously affect the state of another, no matter how far apart they are. At first glance, this seems to violate the cosmic speed limit. but it does not. While correlations appear instantly, no usable information is transmitted faster than light. You cannot send a message through entanglement alone. Causality remains intact. The universe permits correlation without communication. This distinction preserves locality. It ensures that while reality may be deeply interconnected, influence still respects distance and time. The universe is subtle, but it is not reckless. Causality's speed limit also shapes the large-scale structure of the cosmos. Galaxies form because gravity has time to act locally before expansion pulls matter apart. Stars ignite because pressure and gravity interact within confined regions. Life evolves because information spreads gradually, allowing adaptation rather than instant saturation. Even the expansion of the universe respects causal boundaries. Regions of space beyond each other's horizons evolve independently. No signal can coordinate their behavior. This is why the universe can be uniform on large scales without being synchronized everywhere at once. Early causal contact, followed by expansion, sets initial conditions that persist. As you rest, it can be comforting to realize that the universe is not overwhelming itself with its own complexity. It is not trying to do everything at once. It unfolds locally, patiently, letting causes ripple outward at a measured pace. This pacing is what allows calm. If every event could influence every other event instantly, there would be no separation, no privacy, no stability. Every fluctuation would be global, every disturbance would be catastrophic. Instead, the universe compartmentalizes. It allows regions to evolve independently. It limits reach. It creates neighborhoods of interaction. Your own body depends on this. Nerve signals travel at finite speeds. Chemical signals diffuse gradually. Feedback loops stabilize rather than explode because delays exist. Life thrives not despite these limits, but because of them. On cosmic scales, the same principle applies. Supernovae enrich nearby space with heavy elements, but they do not affect the entire universe at once. Black hole mergers send ripples through spacetime, but only those within range ever feel them. Influence fades with distance and time. This fading is not loss, it is attenuation, a gentle weakening that preserves order. Causality also gives meaning to the concept of now. Because signals take time to travel, there is no universal present moment shared by the entire universe. Each observer has their own slice of spacetime they call now, shaped by their motion and location. This does not fracture reality. It enriches it. It allows multiple perspectives to coexist without contradiction. The cosmic speed of causality ensures that these perspectives remain consistent, that no observer sees effects without causes, that time retains its directional integrity. At the edges of extreme physics, such as inside black holes or near the Big Bang, causality becomes more complex. Horizons form, light cones tilt, some regions become permanently disconnected. Even there, causality is not broken, it is redirected. These redirections mark boundaries, not failures. They show where the universe changes phase, not where it stops making sense. As you breathe slowly, consider how rarely you encounter true immediacy. Even thought takes time, even sensation has delay. Your experience is already a collaboration between past and present, mediated by finite speeds. The universe works the same way, only on a grander scale. The cosmic speed of causality is not a constraint to be overcome. It is a quiet agreement that keeps everything from happening at once. It gives space room. It gives time rhythm. It gives events order. Without it, the universe would be loud, frantic, unstable. With it, the universe is surprisingly gentle. And as we approach the final boundaries of this journey, another question begins to emerge, softer but deeper still. If causality itself has a speed and influence must fade with distance, why does infinity appear so often in our equations? And why does nature itself seem to avoid ever fully reaching it? Part 14. Why infinity never fully appears. Infinity exists in equations but never quite in nature. Every attempt to reach infinite density, infinite temperature, or infinite curvature results in a boundary instead. The universe seems to approach infinity, then quietly stop. Infinity is a useful idea. It lets mathematicians extend patterns without end, physicists explore limits, and philosophers ask what lies beyond completion. In equations, infinity behaves obediently. It can be approached, manipulated, even canceled out. On paper, it causes no discomfort. But when physicists search for infinity in the real universe, it never quite arrives. Instead, something intervenes. Whenever a calculation predicts an infinite value, an infinite density, an infinite temperature, an infinite force, it is often a sign that the theory being used has reached the edge of its domain. Nature does not confirm the infinity. It replaces it with a boundary. This pattern appears again and again. In classical physics, point particles were assumed to have no size. When their electric charge was considered, calculations led to infinite self-energy. The solution was not that particles truly possess infinite energy, but that the classical description was incomplete. Quantum mechanics replaced point-like certainty with probability clouds, softening the divergence. In general relativity, equations predict singularities, points where density and curvature become infinite, at the center of black holes, at the beginning of the Big Bang. These infinities are mathematically consistent within the theory, yet physically troubling. They represent places where prediction fails entirely. Rather than accepting infinities as literal, physicists interpret them as signposts. They mark where a deeper description is required. At the Big Bang, density appears infinite when we extrapolate backward using classical equations. But earlier sections of our journey have already hinted that this infinity is likely an illusion. As we approach the Planck scale, spacetime itself becomes unstable. Time and distance lose their meaning. The concept of density ceases to apply. Infinity dissolves not because it is reached, but because the question changes. The universe does not permit infinite compression in open form. It redirects the process. The same is true of temperature. Classical reasoning suggests that heating a system indefinitely should lead to infinite temperature. But as we saw earlier, extreme energy reorganizes matter instead of raising temperature without bound. New particles form, new phases appear. Eventually, temperature itself stops being a meaningful variable. Infinity retreats. Even in space, where the universe may be infinite in extent, infinity never appears as an observable quantity. We do not encounter infinite distances, only horizons. We do not observe infinite age, only finite histories. The universe may be endless, but it reveals itself only in finite segments. This distinction matters. Infinity may exist as a global property, but never as a local experience. Nature seems to prefer asymptotes over endpoints. Values are approached, never attained. Speeds approach the speed of light, but never reach it. Energies increase toward limits, then transform. Curvature intensifies, then hides behind horizons. Infinity becomes a direction, not a destination. This behavior is deeply stabilizing. If infinities were physically accessible, small changes could lead to catastrophic consequences. Predictability would collapse. The universe would not be able to sustain structure. Instead, boundaries appear. Black holes are a perfect example. As matter collapses, density increases. According to classical theory, it should become infinite at the singularity. But before this infinity can influence the outside world, an event horizon forms. Information is sealed off. The infinity, if it exists at all, is quarantined. This is not an accident. It is how the universe preserves coherence. In quantum field theory, infinities appear frequently in calculations. Physicists deal with them through a process called renormalization, which systematically removes unphysical divergences and replaces them with measurable quantities. This technique works astonishingly well, suggesting that infinities are artifacts of description, not features of reality. Nature does not explode when equations diverge. It remains calm. This calmness hints at a deeper principle. Perhaps infinity is not something that exists, but something that guides limits, a marker of where one description must give way to another. From this perspective, infinity is a shadow cast by incomplete understanding. Even time, which feels unbounded, is experienced only in finite steps. Moments follow moments, memories accumulate, futures branch. There is no instant where all time exists at once. Infinity does not appear as an experience, it appears only as an idea. As you rest here, you are not surrounded by infinite sensations. You feel finite warmth. You hear finite sounds. Your awareness moves gently from one thought to the next. The universe presents itself in portions, not absolutes. This may be essential for meaning. If everything were infinite, nothing would stand out. Contrast would vanish. Choice would dissolve. Infinity, paradoxically, would erase significance. Limits create structure. They allow beginnings and endings. They allow comparisons. They allow stories. Physics has gradually learned to treat infinities with suspicion. Whenever one appears, it is treated not as an answer, but as a question. What assumption led here? What scale was ignored? What interaction was left out? So far, every time this question has been asked seriously, a boundary has emerged, a smallest length, a maximum speed, a horizon, a quantum of action. The universe seems engineered, not by design but by necessity, to avoid infinite quantities in practice. Even mathematics reflects this tension. Calculus relies on infinitesimals, yet physical measurements always yield finite values. Limits exist in theory, but experiments return numbers. Precision increases, but never without cost. This suggests that infinity is a tool for thinking, not a substance of nature. There is something quietly reassuring about this. It means the universe is not brittle. It does not depend on unreachable extremes. It operates within ranges that preserve continuity. Infinity may frame our questions, but boundaries frame our answers. As cosmology and quantum physics continue to merge, many researchers suspect that a complete theory of reality will eliminate true infinities altogether. Singularities will be replaced by finite processes. Divergences will soften into transitions. What looks infinite from one perspective will resolve into something bounded from another. This would not diminish the universe. It would make it more coherent. As you breathe, notice how your own experience mirrors this. You can imagine infinite possibilities, but you live through finite moments. You can think endlessly, but each thought has a beginning and an end. Your awareness flows within limits, and those limits make it navigable. Perhaps the universe works the same way. Infinity exists as a guidepost, reminding us we're not to literalize our abstractions. The universe does not rush headlong into infinity. It approaches, pauses, and reshapes itself. And as we reach the final stretch of this journey, one last question waits quietly ahead. If infinity is never fully reached and boundaries always intervene, what ultimately happens when those boundaries are crossed, not by distance or energy, but by curiosity itself? Part 15. What happens if you try to cross the limits? When boundaries are pushed too far, reality responds. Not with explosions or warnings, but with silence. Information hidden, measurements blurred, paths closed. These limits are not punishments. They are the rules that allow a universe at all. Throughout this quiet journey, each limit has revealed the same pattern. When curiosity presses forward, the universe does not break. It reshapes the question. When motion approaches the speed of light, time stretches. When energy concentrates too tightly, horizons form. When measurement becomes too precise, uncertainty rises to meet it. The response is never dramatic. It is subtle, structural, and final. To cross a limit is not to be stopped by force. It is to discover that the path no longer exists. Imagine accelerating forever, adding energy again and again, determined to outrun every boundary. As speed increases, time slows, lengths contract, energy piles up, and then, without ceremony, further acceleration stops changing speed at all. Motion transforms into mass. Effort no longer produces progress. The universe does not forbid your attempt. It simply changes what forward means. This is how limits behave. They are not walls. They are asymptotes. The same is true when we try to look deeper than space allows. Push resolution beyond the Planck scale, and space-time itself begins to fluctuate. Coordinates dissolve. Distance loses meaning. There is no smaller place to point to. The question, where, stops applying. The universe answers not with denial, but with ambiguity. When we try to concentrate too much energy into too small a region, gravity responds. Space-time curves inward, horizons form, information disappears from view. The universe does not explode under the strain. It seals itself off, quietly protecting its larger structure. This response feels almost gentle. Black holes do not announce themselves with alarms. They emerge naturally from equations, inevitable once certain thresholds are crossed. Their boundaries are smooth. Their formation obeys conservation laws. Even their evaporation follows precise rules. Trying to cross a limit does not lead to chaos. It leads to containment. Even knowledge itself is treated this way. When we ask questions that demand perfect certainty, quantum mechanics does not refuse to answer. It answers probabilistically. It offers distributions instead of values. It blurs one quantity as another sharpens. Information is not destroyed. It is redistributed. The universe does not hide out of hostility. It hides out of coherence. This becomes especially clear when we consider horizons, not just around black holes, but everywhere in cosmology. Beyond the observable universe lies silence, not because nothing exists, but because causality has not connected us to it. Light has not arrived. Information has not crossed the gap. The universe does not rush to fill that silence. It allows it to remain. Crossing a horizon does not reveal forbidden knowledge. It removes access entirely. This is one of the most important lessons physics has taught us. Limits are not arbitrary. They are emergent features of a universe that must remain internally consistent. If information could escape black holes freely, causality would collapse. If energy could concentrate infinitely, space-time would tear itself apart. If certainty were absolute, measurement would no longer be an interaction. If infinity were reachable, prediction would fail. Every boundary protects something deeper. From this perspective, limits are acts of preservation. They preserve causality. They preserve stability. They preserve the distinction between past and future. They preserve the possibility of structure. Without them, the universe would not be dramatic. It would be incoherent. As you lie here, it may be comforting to notice how rarely you experience true obstruction. Most of the time, you simply encounter transitions. When you grow tired, consciousness fades. When you wake, it returns. When you push your body too far, it responds with rest, not rupture. Your own biology is full of limits that serve the same purpose. Too much stimulus becomes numbness. Too much exertion becomes fatigue. Too much focus becomes blur. These are not failures. They are protections. The universe behaves the same way. When curiosity reaches its edge, the universe does not shout no. It whispers different. Different equations, different descriptions, different questions. This is why progress in physics so often comes from rethinking assumptions rather than overpowering nature. We do not cross limits by force. We cross them by changing perspective. Newton's laws did not break at high speeds. They softened into relativity. Classical determinism did not shatter at small scales. It transformed into quantum probability. Space did not end at the Big Bang. It changed character. Each time, what looked like a boundary became a doorway, not into unrestricted access, but into deeper structure. And yet, some limits remain absolute, not because we lack imagination, but because they define what imagination can coherently describe. You cannot send information faster than light. You cannot observe beyond a horizon. You cannot reverse entropy on macroscopic scales. You cannot extract infinite detail from finite systems. These are not technical challenges waiting to be solved. They are features of reality's architecture. Crossing them is not forbidden. It is undefined. When you ask what lies beyond a limit, the most honest answer is often that the question itself no longer applies. There is no beyond in the way we instinctively mean it. Just as there is no north of the North Pole, there is no farther than certain boundaries allow. This realization does not shrink the universe. It clarifies it. It tells us that the cosmos is not an unbounded playground where anything goes. It is a structured environment where freedom exists within form, where exploration is possible because limits give shape to paths. Without limits, nothing would hold. Without horizons, nothing would persist. Without boundaries, meaning would dissolve into noise. The universe allows complexity not by removing constraints, but by layering them. As this long journey comes to rest, it may help to sit with one final gentle thought. Every limit we have explored, speed, distance, size, energy, knowledge, time, serves the same quiet purpose. They make existence possible. They allow stars to shine without exploding instantly. They allow atoms to form without collapsing. They allow time to flow without contradiction. They allow stories to have beginnings, middles, and ends. The universe does not resist understanding. It guides it. And when understanding reaches a boundary, the universe does not close itself off. It invites humility. It reminds us that knowing is always relational, always situated, always partial. That is not a weakness of reality, it is its grace. As you rest now, surrounded by a universe that holds together because it knows where to stop, you can let curiosity soften into calm. There is nothing you need to cross, nothing you need to force open. The limits are already doing their work, quietly, endlessly, making space for everything that exists, including you. As this quiet journey comes to rest, the universe feels a little less distant. Not because we have crossed its boundaries, but because we've learned why they are there at all. Every limit we explored tonight, the speed of light, the edges of observation, the smallest lengths, the deepest horizons, was not a wall meant to keep us out. Each one was a structure holding reality together. A gentle rule that allows time to flow, stars to shine, and moments to exist without unraveling. The universe does not rush. It expands patiently. It reveals itself slowly, and it protects its deepest truths, not with force, but with silence. Even now, as you rest, you are safely within those limits. Gravity holds you. Time carries you forward. Causality keeps the world coherent. The same rules that shape galaxies are quietly shaping this moment, allowing it to exist at all. There is comfort in knowing that not everything must be reached, measured, or crossed. Some things are meant to remain distant, not as mysteries to solve, but as boundaries that make meaning possible. The universe is vast, but it is not careless. It is powerful, but it is not chaotic. And within its limits, life finds room to breathe. If this calm exploration has brought you a sense of peace, I'm deeply grateful you spent this time here. Your quiet presence means more than you know. For now, you don't need to think about edges, horizons, or endings. You can let your thoughts drift. Let the scale soften. Let the questions fade. The universe will keep turning. The limits will keep holding. And you are free to rest, gently carried by it all. Good night.